you. Thank you, Kosik, for the introduction, and thank you all for coming. It's really nice to see so many of you. So today I will be presenting the results of my thesis titled Market Design for Future District Heating Systems. And to start with, I will go into some of the terms in this title. So to begin with, what are district heating systems? So those can consist of heat generators, as well as consumers of heat, and possibly also heat storage. And these are connected by an underground piping network, where a supply network transports hot water from generators to consumers, and the cold water is returned back also to in a return network. District heating is expected to play an important role in future carbon neutral energy systems, and that's for two main reasons. The first one is that district heating can help to integrate certain types of carbon neutral heat sources that are not suitable for individual heating. Those include, for example, excess heat, that is a byproduct from some other process, or also renewable heat, such as solar heat and geothermal heat. The second reason is that it's often envisioned that district heating should provide flexibility to the power system, because these two systems are physically linked. First of all, by, for example, combined heat and power plants that produce both electricity and heat, and also by heat pumps that use electricity to generate heat. When such carbon neutral sources will be integrated in future district heating systems, this will have the effect that there will be more fluctuations in the generation cost of this generated heat, and also the available capacity of these sources fluctuates more. And for this reason, there is also a need for demand-side flexibility in these future systems. And these can, for example, come from prosumers that, for example, could have a flexible space heating demand. And there could also be dedicated thermal energy storage devices. And this demand-side flexibility could then also be used to provide this flexibility to the power system. If these changes are to happen, it is expected that the coordination of this district heating system will be more complex than it is currently. And also, it could be that there is an increased potential for competition in these systems. This brings me to the topic of heat markets. Currently, heat markets are highly regulated, and this is because usually there are only a few large suppliers, and they are owned by sometimes even by a single firm. And in such systems, there could be lack of competition, and therefore exertion of market power and market inefficiencies. In current systems, consumers usually pay a fixed price of heat. Sometimes it differs per season, but it's fixed over longer periods of time. And prices paid to generators are regulated, for example, using price caps or profit rules. Then why want to move to liberalized heat markets? Well, a first reason would be if there is enough competition in these systems, then liberalized markets can provide incentives to reduce the generation cost and thereby reduce the price of heat in these systems. A second reason is if we want to activate this demand-side flexibility that we'll need, the market can be the link between the generators and the consumers to activate this demand-side flexibility. And finally, the market can also provide the link to the electricity system, that the heating system will be able to provide this flexibility to the electrical power system. In this future district heating system, we observe three main challenges that we will address in this work. And the first one is that there will be much more small generators and prosumers present in this system. And this is a challenge because this increases the scheduling complexity in the system. And also some of these agents have as a special property that heat is actually not their main business. Therefore, we define as a research direction 1, scheduling and pricing for many small heat producers. Towards this first research direction, we investigate the performance of an alternative to direct market participations of a specific type of these small new heat producers, namely excess heat producers. And the alternative that we study is self-scheduling based on a price signal. In this work, we quantify the suboptimality of this self-scheduling method with respect to a benchmark. And we do that in a realistic case study of the Greater Copenhagen district heating system. Another contribution in this work is that we propose a quite simple district heating system model while still considering electricity price dependence of their bits. The second challenge that we observe is that the heating system will become more distributed. And this is a challenge because it makes network feasibility of market outcomes non-trivial. And it also makes it more hard to guarantee cost-efficient transport of heat in the network. Therefore, we define as our second research direction the network-aware market design for distributed district heating systems. Towards this research direction, we propose a network-aware heat market design, and we focus here on its ability to harness prosumer flexibility. The mechanism that we propose is loss-aware, which means that we estimate and price the network heat loss. And finally, we add peer-to-peer trades to this mechanism, which allows us to trace losses in the network back to pairs of producers and consumers, and thereby we increase the transparency of this mechanism. The third and final challenge we observe is the presence of storage, both in dedicated devices and also in the pipelines of the heating network. There can be storage present. And this is challenging because the market integration of storage remains an open question of how this optimally is done. And the challenging part of this market integration is the time linking constraints that come with storage devices, which makes it necessary to deal with end of horizon effects. Therefore, we define as the third research direction the market integration of non-merchant storage, which I will define later on. Towards this third research direction, we look at this specific market design and in the market integration of non-merchant storage. And there we analyze the market properties of this market design, first on their simplified end of horizon decisions. And then we move on to a situation where we take future aware end of horizon decisions and again analyze the market properties. And a final contribution is that we show that still the future aware approach can lead to a problem with the pricing of stored energy. And there we provide a set of sufficient conditions for this problem to happen and also support this with proofs. The contributions of this thesis are based on three main publications, where the first two are already published in peer-reviewed journals, and the third one is currently under the second round of review. This project was also part of H2020 European project called Embers, where a platform was built to match excess heat and cold. And there we were responsible for the market module. It was one of the sub-modules of this platform. And we implemented some of the market designs that we designed in this project. So I will now move on to go into each of the research directions in more detail, and I will close up with conclusions and directions for future work. So first, scheduling and pricing for many small heat producers. And as I said here, we will focus on excess heat producers because these agents may be actually price responsive, and that's what we were interested in this work. Excess heat is expected to be able to cover a great share of the load in future district heating systems. For example, for the city of Copenhagen, there's a study that has estimated about 50% of the heat load could be supplied by excess heat by 2050. And this excess heat can, for example, come from industrial processes and biorefineries, but also from waste incineration and also refrigeration systems, for example, in the service sector. However, although currently there's already a lot of excess heat available, most of it is untapped. And some challenging aspect of these agents is, first of all, that they're usually of a smaller capacity and lower flexibility than conventional generators. And as I already said, their selling of heat is not their main business, but it's kind of a side project for them. So what we observe here as a barrier for their integration is that it's not so clear how to schedule and price such agents, and in particular when there are many of them. So in this work, we investigated how to schedule and price excess heat. And we investigated two paradigms. The first one is their direct market participation, which has as an advantage that here their scheduling is coordinated with other market participants, so we can come to an optimal scheduling. However, as I mentioned, this might be not so relevant for small producers because the transaction cost of market participation may be too high. So as an alternative, we study this self-scheduling method based on a price signal that is sent to these excess heat providers by the market operator. A disadvantage of this approach is that we lose this optimality of the scheduling because the scheduling is no longer directly coordinated alongside the other market participants, but it may be more relevant for small producers. And the particular question we are trying to answer here is how does the suboptimality of the self-scheduling method actually develop with increasing excess heat penetration? We do that in a realistic case study of the district heating system of Copenhagen, which currently consists of 13 combined heat and power plants, and we add to that a variable amount of excess heat. And here we're assuming it's cooling-based excess heat using heat pumps. And we simulate both the market participation model and the self-scheduling model for a full year. As input data, we use the total heat load of this system, the electricity price, and also the ambient temperature. And for all of these inputs, we're assuming perfect foresight. In the market participation model, the market operator clears the market. And the market participants, here denoted by I, have to submit bids consisting of a cost function and a feasible region. And these bids, they are submitted based on the electricity price forecast. And the market operator clears the market based on these bids, but also on a load forecast of the heating system. And when the market operator clears the market, we obtain a scheduled generation for all the market participants for all the time periods considered, and a uniform price of heat for every time period. In the self-scheduling model, however, the excess heat providers are now self-scheduling their heat. So they obtain a price signal from the market operator, and also taking into account the electricity price forecast, they now make a self-schedule of their heat generation, and they submit that to the market operator. At the same time, the remaining CHPs, they are still submitting the bids also to the market operator. And again, the market operator clears the market, where now the schedule of the excess heat providers is a parameter in this optimization problem and no longer a variable. When the market operator clears the market, we then additionally obtain the CHP schedules and a uniform price of heat. And this price of heat from the market is only used to remunerate the CHPs, whereas the heat price signal from here is used to remunerate the excess heat providers. As a price signal in this study, we used a signal that comes from the district heating system of Stockholm, where they're using an outdoor temperature dependent price signal that you can see here. So here we can see the heat price on the y-axis and the outdoor temperature on the x-axis. And it can be seen that the higher the temperature outside, the lower the price of heat that they will receive. And this is because usually the heat load in the system also follows this pattern. So this function we use to map the input of ambient temperature to a time series of the heat price signal. Then as a result, we simulate the total generation cost for different capacities of installed excess heat. And we do that for both the self-scheduling and the market participation model. And what can be seen here is that for both models, the total generation cost decreases as we integrate more excess heat. And also we can see that the market participation model always has a lower total generation cost, as expected from this perfect benchmark. On the left-hand side, or the right-hand side, the difference between these lines is plotted, where we see the suboptimality in terms of total generation cost of the self-scheduling method. And we see here for this case study, it increases approximately linearly. However, because the benchmark's total generation cost is also decreasing with installed excess heat, the relative suboptimality of the self-scheduling method increases much faster. And this is what we show here. So here we also normalize the suboptimality by the total generation costs. And because of this big increase in relative suboptimality, we in this work conclude that at high penetrations of excess heat, this self-scheduling method does no longer suffice and more advanced coordination is needed. We find that the suboptimality results from two main effects. The first one is that the CHP plants will scheduled in more expensive hours than necessary when they would be coordinated with the excess heat providers. And the second is that the excess heat is scheduled without knowledge of the total heat load in the system. So there may actually be wasted excess heat if this self-scheduled excess heat exceeds the total load in the system. The advantages of this self-scheduling method is that this price signal that's used is very transparent and also interpretable. And also, as said, that the procedure may be easier for many small excess heat providers. So we would advise to try to preserve those properties in a more advanced scheduling and pricing methods. Then I will move on to the second research direction, network-aware market design for distributed district heating systems. So it is expected that future district heating systems will become more distributed due to the integration of some new participants in these systems. The first two are excess heat and renewable heat, and they can be located anywhere in the system. And also proactive consumers or prosumers are also located throughout the district heating network. As a result of this different system setup, the network feasibility of dispatch that comes out of the market is no longer trivial because there are many more configurations possible. And also the cost of heat transport will vary more between different sources that can supply the same consumer. In this work, we argue that those challenges call for a network-aware heat market. And we are focusing here to have this network-aware market also suitable for systems where there are possibly many distributed generators and flexible prosumers. Network constraints would be added to the market, first of all, to guarantee network feasibility so that the outcomes from the market can actually be accommodated by the network. And the second would be to account for heat loss. So we would like to price and estimate the losses related to a certain heat consumption. So in this loss-aware market design consisting of two components, we have an optimal dispatch component where we will model the network dynamics to ensure feasibility and minimize losses. And in the pricing, we want to include the cost of the loss in the network. The first question we had to answer in this work was how to model the district heating network. Here we can see a supply network where you can see different nodes and they are connected by pipelines. And we're also assuming that a greater grid is connected to this more local network. There's also a return network that is symmetric with the supply network, but has opposite flows in the pipelines. And a single node consists of a supply side and a return side that you can see here. A node can be a net load or a net generator, and that depends on the flow direction in this node. If the flow is from the cold side to the warm side, then this node is heating up this water, so it's a generator. And if the flow is reversed, it's a load. We are assuming a radial network and also unidirectional flow in the pipelines, which is very common for existing district heating systems. But the flows within the nodes can be bidirectional. There are a lot of possible variables in a system like this, such as flows and delays of the water in the pipelines, also its temperature, the pressures in the system, the pumping power, and the loads and generations. But if everything is kept variable, then this model becomes a mixed integer nonlinear program. The nonlinearity comes mainly from the mixing equation, which models the temperature at a node when two streams of water come together in this node. And this is a bilinear equation if both the flow and the temperature are variable. And the combination of variable delays and variable temperatures leads to the integers in the formulation. In a market context, we often prefer a convex formulation because this allows us to guarantee that we find a global optimum and also that we can use the meaningful dual variables in the formulation for pricing. So the next step is to choose a convex version of this model. Here we considered 3 different options, where the first one was to apply a convex relaxation while keeping both the flow and the temperature variable. This would be the most accurate and most flexible formulation, but it already becomes computationally intractable for relatively small systems. So we needed to simplify that. Then there are 2 options, either to fix the flows or to fix the temperatures in the system, which have both some loss of accuracy and flexibility, but we gain computational traceability. The first one of these 2, the constant flow and variable temperature model, has the disadvantage that the power injections at the nodes already become rather fixed, and especially the direction of the flow in the node already has to be fixed, so it's already decided if it's a load or a generator. And therefore we decide to go for this final formulation with variable flow and constant temperature. This comes at the price that there's no longer free injection temperature for the nodal generators and consumers, but we gain more flexibility. So in this approach, we have the variable flow and constant temperature model, where we fix all the nodal temperatures, so both at the supply side and at the return side, and the temperatures are fixed over time. And we show also in this work that this leads to a multiplicative loss formulation. So that means that if we take a pair of nodes, then the share of energy that's lost on the way to the next node is a fixed share. We still assume this unidirectional pipeline flow, but we allow for bidirectional nodal flow, which allows us to have prosumers. And it's possible to have multiple points of heat injection. And the final formulation has all linear constraints. To show the workings of our market design, we designed an illustrative case study where we compare the proposed design, where we have a loss-aware market that minimizes the total generation cost. And we compare that to a benchmark that we design. And this benchmark is also network aware. So the outcomes of this benchmark are also feasible in the network, which allows for fair comparison to our proposed market. But in this benchmark, we make it ignorant to the cost of network heat loss. So we remove that network heat loss cost from the objective function. To compare the 2, we look at this small case study where we have 11 nodes connected in a line. We have a connection to a greater grid at the first node, and we place local heat pumps at the first node and at all the even nodes. And at all the odd nodes, we place consumers. And we specify the marginal cost of these heat pumps artificially so that they have increasing marginal costs as we move away from the grid node. Then we look at a simple case study where we simulate for 24 hours, and we look at the total scheduled heat generation for each of these nodes, and where we remember that the most expensive heat pumps are located distant from the grid node. If we first look at the loss agnostic benchmark in orange, then you can see that this loss agnostic benchmark tries to schedule the cheapest heat pumps first, as long as this is feasible in the network. So this can be seen by this decreasing amount scheduled by the orange bars. For the loss-aware market, we can see that some of this generation is shifted towards the more distant heat pumps. So even though these heat pumps are more expensive, because they have lower losses related to them, the market mechanism schedules the more expensive heat pumps, because they lead to a lower total cost. So we see that this loss awareness favors generators that can be closer to consumer due to lower losses. We also looked at the total cost and the total heat loss in the benchmark and the proposed market. And we see that both the total costs are decreased and the total heat loss in the network is also decreased in the proposed market. So we conclude towards this research direction. We proposed a network and loss heat-aware heat market, where we focused on having it suitable for a system with many distributed generators, and also the integration of prosumers and the harnessing of their flexibility. We show that the market can ensure feasibility, also reduce total generation cost by reducing the losses in the network, and it thereby promotes also a more local consumption. Now we'll move on to the third research direction, market integration of non-merchant storage. We are distinguishing three market design categories for the integration of storage, where the first one is we call self-managed merchant storage. And this corresponds to the way storage typically participates in electricity markets now, where they submit price quantity bids like other market participants. So this means for storage that they submit a cost curve and they submit discharge limits. And in this paradigm, the storage operator itself has to ensure the feasibility of the schedule that comes out of the market. And so by placing the bids correctly. As an alternative, one could consider what we call market managed merchant storage, where the storage is still submitting price quantity bids, but now also storage operational constraints are considered in the market clearing optimization. And this moves the responsibility of feasibility of the storage schedule from the storage to the market operator. And as a third alternative, we consider what we call non-merchant storage. And this has the difference with the previous category that no longer a cost curve is to be submitted. So this time only discharge limits and also storage operational constraints are considered in the market clearing. The idea behind this not submitting a cost curve is that the marginal cost that the storage have actually comes from the market, from purchasing energy in the market. So in this setup, the storage would be co-optimized to achieve maximum social welfare. This last non-merchant storage formulation is especially relevant for the heating system, because the pipeline storage in district heating networks can actually be considered as a non-merchant storage. And that would appear in certain types of network-aware heat market designs. So it links back to the previous research direction. But also for just storage devices, it is an attractive formulation to efficiently integrate storage while respecting its operational constraints. A challenge with the non-merchant storage formulation is that the time linking constraints that come with storage that normally are part of the optimal bidding problem of the storage itself, they are now transferred to the market formulation. Those time linking constraints in the market are challenging because markets are cleared for subsequent finite horizons, but due to the time link constraints, these subsequent horizons are now linked. And that can first of all be seen through the final state of energy in the current market horizon. It has an effect of the possible market clearing outcomes for tomorrow. So here we see a curve, a state of energy curve over time, where we see two market cleared periods. And we can see that the final state of energy, it has an effect of the paths that are possible for the next day. Also, it links back that the decision on what would be an optimal final state of energy in the storage for today's market clearing depends also on what we know about tomorrow's market clearing. And the challenge is that this information about tomorrow's market clearing are not available at the moment that the decision has to be made. To bypass such challenges, it is common to take some simplifying assumptions, which means that we move into some kind of myopic decision making, where we do not take any information that we may have about the next clearing into account. And another approach would be to do this in a future aware way. So in that case, one would take some kind of information about tomorrow into account. In this work, one of our aims was to draw attention to these end of horizon issues related to the non-merchant storage. And we also wanted to analyze the effect of these different types of end-of-horizon decisions on desirable market properties. So we do that both under, in the case where we look at simplified end-of-horizon decisions, and in the second case, we take a future-aware approach. The market properties that we are looking at are first that of cost recovery, which means that all the market participants recover their cost. The second property of market efficiency is guaranteed when two sub-properties are guaranteed. The first one is that of dispatch following incentives, which means that the market participants do not have an incentive to deviate from the market outcomes. And the second is that the social welfare is maximized by the market outcomes. The market design that we're looking at here, we have a linear objective function, which is to maximize the social welfare. And we emphasize here that we're not including any cost curves for the storage there. And as constraints, we have a storage model that I will specify in the next slide, as well as generation and consumption limits and a power balance. And the dual variable related to the power balance is the uniform price that we are using in the market. And this price is also used to remunerate the storage. So the storage is paying this price when it's charging and paid this price when it's discharging. The storage model that we're looking at, we are modeling the state of energy E and how it evolves over time based on the charged energy B. And for the initial update equation, it also depends on the initial state of energy at the market, start of the market clearing. And after that, we keep updating this state of energy in the battery. So here you can see the time linking constraints appear. We also pose state of charge limits. So the energy in the battery has to be constrained between lower and upper bounds. And depending on the approach, one may also include an end of horizon constraint that we here formulate as setting the final energy level in the battery to a fixed constant that is chosen by the market operator. So in the future aware approach, you would choose some suitable value of this E end based on information about the future. However, in a more myopic approach, there are two main ways of dealing with this end of horizon constraints that we see in the literature. The first one is do nothing. So we do not add this constraint at all. And this usually leads to a profile that could look like this blue one, which means that the battery will be empty or the storage will be empty by the end of the horizon, because it's just optimized to maximize social welfare locally on the single day. A second constraint often included is to have the start and end level of the storage equal. So this E end would be chosen to the initial level, and that could, for example, lead to the green profile here. So the first we did was to analyze the market properties under these two simplifying assumptions. And we found that an advantage actually of doing this is that cost recovery is ensured for all market participants, even within each market interval. However, dispatch following incentives and maximum social welfare are not guaranteed. And this you can maybe understand from looking at these two curves, where the black one is the perfect state of energy profile that would maximize social welfare. And the blue one is a result of one of these myopic approaches. And we can see that the battery is kind of underused here. And this means that usually the storage can improve its profit by moving towards this this perfect curve. And also moving towards the perfect curve would usually increase the social welfare as well. So due to these two properties not holding, market efficiency also does not hold. Then we move on to the future aware case. And to analyze the market properties here, we looked at a two horizon case that we clear in two different ways. The first one is we call the full horizon problem, where we clear both the horizons at once. And this we consider as an ideal benchmark, because the market is cleared while actually already including the next day's information. The second one is the split horizon problem, where we clear the two horizons sequentially, one horizon at a time. And we do that in a future-aware way, which means that we set a certain, so we enforce a future-aware end of horizon storage level. Actually, we take that one step further here, and we assume that we have perfect foresight about what is the optimal level that we should constrain the battery to take. And we do that because we want to show that the loss of market properties that we obtain, it's not a result of imperfect scheduling of the battery, but it's actually a result, an inherent result of splitting the market. So first we look at the primal solutions in these two different cases. And we show that when we take this horizon problem with perfect foresight, we actually obtain the same set of primal solutions in the perfect foresight split horizon problem and the full horizon problem. So this profile would be obtained again with the split horizon. However, we also observe, we do observe an effect on the dual solutions. And the reason for that is that the split horizon problem lacks a dual equation compared to the full horizon problem. And as a result of that, the split horizon problem may actually admit additional solutions compared to the full horizon problem. And that is a problem because some of those additional solutions may be weak, which we mean non-dispatch supporting. And in this work, we formulate a mild set of conditions under which those weak solutions are guaranteed to exist. And we prove that based on corresponding conditions. So due to the existence of those weak solutions, we do not guarantee cost recovery in this market design, not within each market interval and also not in the long run. Dispatch following incentives are also no longer guaranteed, and therefore also market efficiency does not hold. Because the primal solutions are equal between the full horizon problem and the split horizon problem, we do have the maximum social welfare under this perfect foresight case. A final contribution in this work is that we restore the market properties while remaining in this future-aware setting. And we do that by restoring this missing dual equation. And that's done by making the initial storage level a decision variable and adding several terms to the objective function, while not changing anything in the complexity of the problem. So it remains a linear program. And as a result, we can then guarantee all of the four market properties. However, the cost recovery is only ensured in the long run and not within each market interval, because the storage may be performing arbitrage between the different horizons. So that brings me to the conclusions and directions for future work. So in this work, we proposed and analyzed different heat market designs, while we were focusing on three main characteristics of future district heating systems. The first is that there will be many small heat providers present in the system, also excess heat providers. The system will be more distributed, and there is a presence of storage. And we want to emphasize that the different designs that we studied are compatible, so they can be combined. For future work, a first direction that could be interesting to take would be the relaxing the assumption of perfect foresight. We took that here in all of the three works. For the self-scheduling work, relaxing this assumption could mean to consider imperfectly forecasted electricity prices, and for example, seeing how that would affect the suboptimality of this self-scheduling method that we investigated. In the network-aware scheduling, one could consider uncertainty in demand profiles or generation profiles, and also make the formulation, for example, robust with respect to these uncertainties. And for the work on storage, one way to deal with the uncertainty would be to find ways to optimally determine end of horizon storage levels based on certain prediction of the future. And another direction there would be to reformulate the market design so that some of the market properties can be guaranteed also under uncertainty. The second direction for future work would be to look for alternatives to the self-scheduling of excess heat providers, because we concluded that that would not be sufficient for larger penetration of excess heat. So alternatives that could be investigated would be, first of all, a heat aggregator that would participate in the market on behalf of these participants, or also energy communities for heat, and also the different services that they could provide. Finally, from the policy perspective, we want to emphasize that district heating systems are different in electricity systems in that they are more localized, and it's not certain that liberalization will be possible for all district heating systems. So one direction for future work would be to develop some tool to actually determine which systems could be suitable for liberalization. If there is not enough competition for liberalization, the mechanism that we studied here could still be used in a more regulated setting. If the answer is yes, so there is a potential for enough competition, then it's important to increase competition in these systems by stimulating the integration of small producers and also activating the demand-side flexibility. I want to thank you for your attention.
Thank you.